So welcome, and we're going to be talking about this idea. So last time we realized that we could get a force on one section of wire using F equals I L cross B. But if I try to do that on two sections of wire that form a closed loop, I get no net force, and the key word there is net. So I have two forces in equal and opposite directions, and so they cancel each other. But they're not going to be in line with each other. And so what we'll get is something like, I'm going to just draw this. If I have a wire loop, I can have a force in that direction and a force in that direction, and there's no net force because the forces are in line and they're equal and opposite. But that doesn't mean to say there's not a torque. Remember, the thing about torque was when forces are not in line. So I do get a torque. So although the sum of the forces equals 0 along any line for a closed loop that's carrying current inside a magnetic field, the torque is not. And so we look at this in a little bit more detail here. And so we say, consider a rectangular loop of a uniform magnetic field. So my magnetic field is going to the right, and I have a square of wire. Let's make it simple for ourselves. And I have 4 edges to this, 1, 2, 3, and 4. And I have a current flowing. In this case, I'm showing the current flowing in a counterclockwise direction as I look at it. And we say we can determine the force on each section of wire. And the first thing to realize is in this top section of the wire, my B is in that direction and my I is in that direction, which means my L is in that direction. Remember, it's I magnitude L cross B. And if my L and B are in line with each other, then I, L, B sine phi, because that's what a cross product is, the sine is of 0 degrees or 180 degrees, which either way is 0. So there is no force on the top wire, and there's no force on the bottom wire. So I can just forget about those two wires. They just make no contribution. So then I can look at the two vertical wires individually. And if I use my right-hand rule, what I'll see is that if I have my B, as I look at the page, going to the right, and my I, my L, so let's draw that. So I is downwards. So that means that L is downwards. And B is sideways. So L cross B means that the force on this guy is coming out. And the way I show that is I show a point like that. So it's coming out. And yes. And then on this one, on this right-hand side, I have my I is going upwards. So that means my L is going upwards and my B is going sideways. So I have L dot B, and that means that force there is going into. There's my force. So I have two forces in opposite directions that are displaced from each other via a distance, and so I have a classic torque situation. If I look from underneath, and if you're using the Survey and Jewett book, then what you'll see is this diagram is there, but it's not labeled actually, but it is looking from underneath. So if you look from underneath, this force, I'm looking here, and this force is pointing upwards, and this force is pointing downwards. And so I get a turning effect. And then, and apologies before we begin, because the book uses little b, which can be confused with big B meaning magnetism, and it uses little a, which can be confused with big A meaning area. So there's like a whole situation where I can have a whole bunch of problems here. For these two vertical arrows, because they're at 90 degrees to each other, F, which equals I, it's going to be L cross B equals I, L, B sine 90. And sine 90 equals 1. And looking at my diagram, then my L can be represented by A. That's my L. So I go not ILB, but IAB. So that's where all that comes from. That comes to A, that comes to there, that comes to there. That's where that comes from, yeah? So, okay. And then I say, well, there's two of them, and they're separated by a distance b. That's the bottom of my loop. So I go, well, my maximum torque when I'm at 90 degrees, when my L is at 90 degrees from my, when my force is at 90 degrees from my lever arm. If I imagine it a little bit later, I will have the same force, but because of the angle, I will have a smaller lever arm. Does that make sense? So that's less torque. So this is the situation for maximum torque, because those are at 90 degrees to each other. And basically I say, well, this is going to be F2, that's the force on wire 2, times its lever arm, which is B over 2. It's perpendicular, so there's no cosine of the angle. Then I have F4, which is this force down here, times its lever arm, which is B over 2. And then I say, well, hold on, F2 is equal to F4, and F is equal to IAB. So 2 times IAB, this is my F. 2 times IAB times B over 2. The 2's nicely cancel. I get I, A, little b, big B. And, oh, little a times little b is the area. So that's the area. So this is the area. And that's for the maximum turning effect. If I go to other angles, all I'm reducing is reducing my lever arm. I'm not changing the forces.
I have a question.
Yeah.
Up here when you said ILB sine 90.
ILB sine 90, yeah.
Sine 90 is, I thought you earlier said sine of 0 or sine of 180.
Yeah, it was a different situation. That was for the top. Okay? For the top, my current and my magnetic field are in line with each other. So that is sine of 0, 180, and that's 0. But now I'm talking about the vertical sides, and it's sine of 90. Yeah. So, okay, cool. So let's stop for a minute. More torque, more current. Makes sense? More torque if you have more magnetic field. Makes sense. More torque if you have more area. Not obvious, but that kind of makes sense. What is a little bit kind of weird is if I have that kind of wire versus that kind of wire, all my physics training says, oh, big lever arm, small lever arm. So my first intuition might be that this thing with a big lever arm, you know, will be better than something with a smaller lever arm at torque, yeah? If you push further away from the turning axis, a given force gives you more torque. And this is saying, no, the torque is independent of how big your lever arm is for a given area of coil. And what's going on there is, yeah, I have a big lever arm, but I've only got a small force because there's only a little bit of L. And here I've got a small lever arm, but I've got a big force because I've got a bigger value of L. So it trades off. So it turns out that, you know, you don't get an advantage by having your coil that way as opposed to that way. Yeah. So this is just a little bit of an intriguing little answer. If I go to a non-standard, non-idealized angle, I'm not at 90 degrees, I'm now at some other angle. All I've done is I've gone from having a lever arm of B over 2 to having a lever arm of B over 2 sine some angle. And the angle they're defining, and we've been in this pattern before, whenever you get coils or Gaussian surfaces, rather than talking about the angle between something and the plane, let's talk about the angle between something and the surface normal. So we define this surface normal area vector, and we compare that with the magnetic field vector. How many times have we done that now? A whole bunch of times. And all we got to do is figure out whether the area vector is pointing up and to the right or down and to the left. And for that, we use yet another right-hand rule. And what we do is we basically say if the current is flowing like my fingers are flowing, then my area vector is pointing like my thumb is pointing. So, great. So this means that, when you have as you look at it, when you have a clockwise current flow, you've got the area vector is pointing out towards you. And so we say, well, torque at a given angle is equal to F2B over 2 sine this angle plus F4 B over 2 times sine of this angle. It's just the lever arm modified by the angular effect. And I know that F2, because there's two of them, F2 and F4 added together gives me 2IAB times the lever arm, which is B over 2 times sine the angle. And so I go and follow this through, and I get the same result I got before, IAB, where A is the area, but it's modified by the sine of this angle. And I recognize this, and I go, hold on, that's a cross product. So I go, oh, this is IA cross B. So let's just think for a second. So we add F is equal to Q V cross B. Yeah. And then we said F is equal to IL cross B. And now we're saying torque is equal to IA cross B, where A is the area and B is the magnetic field. And can you see how we've taken this, let's be frank, although it's just torques and the like, it's complicated mathematically. I mean, if you had to rederive this thing, although you've seen it, we'd probably stumble a few times on the way. Get confused about the angles and all that. We've made it kind of very straightforward. It's just a cross product. You just got to know, how do you define your A? How do you define your B? Get on with it. So it makes what would be a really quite complicated thing into quite straightforward. And from a visualization point of view, having lived on visualization, I kind of feel cheated now, because it's like, anybody can do this. As long as you know how to do a cross product, you can do this. I can throw a really complicated problem at you at some wacky angle. It's just A cross B. It's done. So in a way, it's beautiful. It kind of like, it really helps. So let's do some of these. A 5 Tesla magnetic field is directed on the positive x-axis. Oh yeah, there's the teacher part of me. So this is 5 Tesla. And a 7-loop coil carries a current of 4 amps, and the area vector, let's use the area vector, area is equal to, it's a vector, so that's going to equal 2I plus 3J plus 1K. It's got units, it's meters squared. I don't know where it really points, but I'm just drawing it. And so there's my, if you like, there's my coil. Might as well draw my coil in. Now, if I have one loop, that's 1 times the current has had the effect. But if I keep making the current go round and round and round, I'd expect more effect, because each time it goes round, it's going to have the same effect. So I have to take into account the N, the number of turns, and the number of turns was 7. Let's have a look. And my current, my I, let's do it right way round. There's my I. To give me that A, I need that I. I is equal to 4 amps. So there's my visualization. And then I want to do, what is the dipole moment? Oh, I don't think I told you what the dipole moment was. Let's go back. I skipped that bit. When you see those two together, why not just call them a thing? So you say, okay, we can define the magnetic dipole moment. So it's a vector, and it equals the current, which is a scalar, times the area vector. So we can say torque is equal to mu cross B. And we can even define the dipole for the coil, which is N times mu loop, which is n times IA. And so I can find a torque for the loop, for the coil, which is mu coil cross B. And frankly, I kind of regard all that as, it's the kind of thing where I'm sure if you know how to bowl, but you've never hung out with bowling people, and you sit down for coffee with them, you won't understand what on earth they're talking about. Because they get into the jargon. And the jargon develops because you get shorthand names for everything. If you do it all day long, you just get, a terminology for it. You develop it over time. It's part of being a community. In a way, linguistically, my wife would say, it's a way in which groups define themselves. My wife would say, the reason why that develops is not just because it's shorthand, but also it's because it's like magic code. And if somebody comes up to me and they use the terminology I know, I check them off my anxiety list because they're from my culture. And if they're using correct things, if they're describing, vegetation on a plate that's been steamed, then I know that they're intelligent, but they're not from my culture. They're not calling it veggies, so, it's kind of like I'm wary of them. And then we just got that intuitively in us. And the same thing goes for engineering. Engineers develop this thing, in part because they're just hanging around during coffee time and they're discussing the job they're doing. So they develop this code. But also the thing with a little sting in the tail is if you don't know this terminology, then you'll be regarded with some caution because you're not part of the family until you get this terminology. So it's really worthwhile. That's why reading a book is important. Watching videos is important. Getting the language. You can be as bright as you can be, but if you're not using the right language, then it's a real issue. I don't know if I told you, Trevor Noah. Did I tell you about Trevor Noah, basically? Trevor Noah's mom spoke about 5 different languages, and she was very keen on him. He was in South Africa, very keen on him, not just knowing English and Dutch, but also these other languages, the African languages, the traditional languages. And he was walking down the street, and these guys are about to set on him. And he knows, you can tell by their body language they're going to set on him. And they start, how it goes on. If you've ever been beaten up, in Britain you tend to get beaten up a lot. But people taunt you before they beat you up. They kind of they just have to say something, and they mock you, and then they beat you up. It's a way of dehumanizing you so they can feel better about beating you up. And so they were mocking him before they beat him up. And he, being a good mimic and also knowing the languages, spoke to them not only in their language, because they were using their old home language, but also they spoke to them with the accent and the dialect. And he said they stopped in their tracks and they apologized to him. And they said, "Oh, sorry, we thought you were one of them." And he clearly looked nothing like them. He was, different. Some people are tall, some people are short. He did not physically look like them. He's clearly a different group. And yet, because he spoke in their dialect and in their language, language, his argument is language trumps everything. If you can talk like somebody, you are inside their psyche. So go and talk like an engineer if you want to be an engineer. Go and talk like a physicist if you want to be a physicist. If you want to be an accountant, talk like an accountant. And doors will open for you. If you're bright but you don't talk like the group you're trying to join, it's not going to work. They're going to always put you to one side. Oh well, in that case then, got to tap dance. I don't worry so much about this. What I do is I know I equals A cross B really well, and then I know the mu equals IA, and I can figure the rest out from there. I know that N matters. So sometimes I'll tell my students, especially when they first begin, put down NI cross A, because it's going to matter how many loops you have on this. But, just you can visualize it, and it's okay.
N will be the number of
So
loops.
you have to use N.
N is the number of loops. Oh yeah, if there's 5 loops in it, there's 5 times the effect. So you got to include your N. Logically.
What's the unit for the dipole moment?
Well, let's think about it. What's the unit for I? If mu equals IA, what's the unit for I? And what's the unit for? Yeah, that's exactly right. Yeah, cool. So, well, there's the setup. So then, what is the dipole moment? So mu is equal to IA. And let's look, I have an A, so mu, it's going to be a vector. It's going to be 4 times 2I plus 3j plus 1k. So mu is going to equal 8I plus 12j plus 4k. And it's going to be, as we said, it's going to be amps meters squared. And then what is the coil dipole moment? So mu coil is equal to N IA. Was I saying cross here? It's just IA. NIA. So that's going to equal, let's have a look, number of loops is 7. So it's 7 times 8I plus 12j plus 4k. So that's going to be, oh man, 7 8s are 56, 56I, 7 12s are 84, 84j, and 7 4s are 28, 28k. And N has no units, so it's still going to be amp meters squared. And then what is the vector torque experienced by this? Well, okay, I'm going to turn around and say my vector torque is equal to NI A cross B, which equals NIA is mu coil cross B. So I can do that. I can at least use all this work. So then I go IJK, and I want mu coil. I just worked that out. That's 56 and 84 and 28. But now I need my B. And my B is, it's got to be a vector. Vector B is equal to 5I plus 0j plus 0k. Good old vectors. So then I have 5, 0, 0. And then I put my finger over the 56. So I put my finger over the first bit and I go 0 minus 0 is 0I. Minus, because I'm doing a cross product, put my finger over the middle column and I go 0 minus 140. So 0 minus 140. I get the 140 by going 5 times 28. 10 times 28 is 280, so 5 times 28 is half of it. And that's going to be J. And then I put plus down because I'm doing this kind of stuff. And I'm going to go 0 minus, oh man, 0 minus, and half of 840 is 420. Okay. So that's going to be 0I plus 140j minus 420k. And it's not there, is it? I messed up on that bit. Did I make a mistake, or is it just that I didn't put the right answer down? I think I just didn't put the right answer down. This is certainly right, 500, that's right. And this is 56, 84, 28, that's there, so that's right. And it's new coil cross B. I put my new coil down. So let me just double check this, put that 0 and 0, so that's definitely a 0. And then that's going to be 0 and 140, that's definitely minus 140, minus makes plus. And then that goes is, yeah. So what did I probably do? I probably, I just messed up. I probably, what do you think I did? Didn't multiply by n. Yeah. No, I did here, but in these answers. Yeah, there you go. That should be a plus sign. And yeah, no n. Bad. But it shows one of the classic mistakes is not multiplying by n. So watch out for it. So not so bad. It's just another cross product. And there we have it.